자, 반갑습니다. 네, 오늘 10월 달 마지막 주입니다. 벌써 가을이고, 날씨가 많이 추워졌어요. 내 말 잘 들리나요? 네, 그, 여러분들, 여러 번, 강조하지만은 수업 시간에 특히 이런 온라인 수업에, 어, 여러분들이 그 집중력이 이제 흐트러지기 참 쉽습니다. 그래서 한 가지 부탁을 하는 게, 어, today is the October 30th. Uh, as I mentioned, we will continue to study about the beam theory, especially the beam deflections. Uh, Now, all loads are applied with the boundary conditions that those are given. Uh, and then what we like to do is to calculate deflections. And now once you have a deflections, we will able to get all the stresses. Uh, once you have a stresses, you will be able to design. Uh, Design means that we can make this structure as safe, and we can make this structure lighter, cost effective. So mechanical engineer need to able to design given certain conditions. Uh, we we repeatedly emphasize the importance of understanding this 351 flow chart. Uh, let's say uh, go to the beam theory. We can apply this 3+1 flowchart to the subject we are studying. When when we solve a mechanics problem, we all need to identify what are the given conditions and what will be the outputs. It, it's easier to clarify those two items. What are the given and what we like to solve. And this analysis flow for the beam. So again, 화면 보이죠? This is the beam. Beam means that we have a certain boundary conditions. For example, clamp. In homework, we had a problem that left-hand side we had a clamp. On the right-hand side, we have a simple support. Simple support always use this kind of arrow. And then we can have a sort of any kind of a distribute load. This is very typical. The beam dimensions, say length should be given, and also EI should be given. So this is very typical beam problems. Of course, the boundary condition on the left-hand side and right-hand side, they may vary. We can have a free boundary condition. We can have many different combinations. Now, let's apply this flow chart. The force, now the uh, a materials of a beam. Okay, this is the EI. I would say this is the EI. I is a geometry, but the characteristics wise, this is the all given bending stiffness EI, and then a force. This distributed load we call QX, function of X. This will be the X. So force QX will be given and applied to a beam of EI. And then deformation. We can calculate the deformation. I will say for this kind of case, the deflection will be like this. Say Vx is the one we like to find. Okay, so this will be the Vx we like to find. Also, we can say the for the beam, we have a beam conditions, deformation conditions. Means that on the left-hand side and the right-hand side, we have a sort of a boundary conditions. And now the equilibrium condition, this is the X and Y. Since QX is a distribute applied to vertically, there should be an equilibrium. Equilibrium means that on the boundary, on the left and right, there should be some kind of a reaction force. We don't know yet, but there should be a sort of a reaction force. We can call R1 and R2. Now, another one, see this clamped is especially the rotation should not rotate. So there will be additionally a reaction force. I will say moment 1. Here, just a simple support. The rotation is allowed. So when you draw, I pay attention. I draw like this and that. So this rotation is not allowed and deflection is not allowed. But here, deflection is not allowed, but the rotation is allowed. So there is no reaction moment. So anyhow, the equilibrium, these are unknown. So equilibrium means that this beam, the vertical forces, all the vertical forces in y direction should be 0. And this total whole beam should not rotate. The moment, say z equals 0. This is the equilibrium condition. And the strain, once we have a Vx with the boundary condition, the strain, we already know that epsilon x will be, the minus r over y. This is the from beam theory. And the stiffness, we do have a EI from given. And to solve all this, and then the stress will be not always, but the for this case will be, of course, the force divided by cross sections, and then multiply y, and there should be a minus. Sometimes, so you need to remember this and that, or you should be able to drive or always. But it's important. And then once we have a stresses here, this stress should be less than strength. strength means that we have a yield strength. This material will have a yield strength and has to be less than yield strength. So the moment, the stress is a moment it will be a function of x, and the y means the vertical direction. And I can be x function, but let's say it's a constant. So sigma, to find the maximum sigma, we need to find the maximum moment. Moment where does the maximum occur? That is the first step, important, right? So the find maximum uh, maximum moment and its location. This is the very critical. The reason is that to get the stress, uh, uh, we should first find the maximum moment. And then, of course, the maximum stress will occur at the top or bottom, right? So once we have a location, say a certain point here, the moment will be maximum, then always a stress will be like this. This will be the top and bottom, there will be a maximum and minimum compression. So this stress should be less than yield strength. This is very typical procedure of design. So any beam, the bridges or any structure in automotive or any structures of UAV, eVTOL, or airplane. Speaking of the eVTOL, let's say I like to emphasize the importance of eVTOL. eVTOL means that uh, you can find out what does it mean eVTOL to eVTOL. eVTOL stands for electric vertical takeoff and landing. You saw the many times the drone. Uh, And in short, we call eVTOL or EV. Sometimes it's called flying car. It's very important to understand these eVTOL structures. We mechanical engineers should be able to design. This is already been developed by Hyundai, many the big company, and then also small startup company. They developed in Korea, in China, and all over the world. Is technology-wise, it is very demanding, but uh, they are actually well developed, as you can see that the uh, sometimes unmanned, but mostly the men. This is a flying car, and even in Korea, there will be a service from Seoul to Incheon Airport. You will take the very quickly, say order of say 10 to 20 minutes. We can save a lot of time and very convenient. So by the time you graduate and then you go out to industry, by that time I hope that these structures is approved uh, and then get certified and really fly. Uh, we hope that they are in service very soon. Uh, so as you can see, how this structure work. Oh, there will be, as you can see, Joby is the most number one the company in United States. They already approved that. Approval is very important to be in service. All kinds of regulations and you know very demanding. And you can get the price. Well, price we don't. I would say if you are rich enough someday, or even now, you can buy one and you can have your own eVTOL. Uh, and say Toyota also have a one, and Joby, as I just mentioned, that you can look at their stock value. The stock increase a lot. Okay, the one thing I like to emphasize is that battery. See, their power system, they are using the battery like this. A similar battery which are being used in a electric vehicle. So they are using the battery types. And the main reason why they use the battery, not the regular fuel, is that the is operated by the all motors. Uh, all the motors. One, two, three, four, five, six, all motors. Now we need electric power, and so that we can directly get the power to rotate all the motors. But the disadvantage of the battery is that it simply is really heavy. The structures have to be very light. That's a very important feature of the transportations. Unfortunately, the batteries are really heavy. Well, even in automotive electric vehicles, the battery is the one bottleneck, very heavy. You should be able to make it lighter. That is the one thing we need to do. Well, you can browse all kinds of Joby Aviation and the legacy of Uber.
Joby Aviation is taking the legacy of Uber Elevate and turning it into reality. Are flying taxis finally on the horizon? Today, we'll explore the thrilling developments in flying taxis, focusing on how Joby Aviation is stepping up after Uber Elevate's ambitious plans. What new ways will we have to travel over city traffic? Let's jump in and find out what's next.
Well, I like to emphasize is that
The dream of flying taxis is closer than ever, especially with Joby Aviation acquiring Uber Elevate. This deal marks a significant shift in the urban air mobility landscape. While the financial details of the acquisition haven't been disclosed, Uber has committed an additional
So many different types. Okay, many different types. Uh, so in this beam theory, I like to emphasize that the structure consists of many different the beam structures. Say As you can see that this is the main weight. There will be a lot of weight here. And then if we have a, let's say, consider one of the beam, uh, and then this will be certain conditions. Say we will have a certain the force upside, and the sometimes the moment, and the sometimes distributed load here. So this can be called the beam structures. Uh, I'm sorry, let me find a better pictures showing all types. Say eVTOL. Oh, Yihang is the one Chinese the eVTOL, and these structures would uh, have a better beam structures. I mean, it's a so Yihang is the another company who get all the certified the eVTOLs. They will have a start the service very soon. So anyhow, we have one, say one, two, three, four, five, six, seven, eight structures. And if we pay attention to these structures, we can see that at the center, this will be a heaviest part. There will be a weight. Or we can just consider this is the clamped conditions, and then there will be some vertical load. If we pay just attention to a beam structure, this is the, by the way, as you can see, the main structures working as a beam. Of course, there will be a sort of a little bit of a distributed load. But in this case, distributed load is not that much big compared to just the regular airplane. But most likely, this is at the tip, we have a vertical load and with clamped conditions. We can say this is the structure look like this. I'll say like that. Let's neglect. Okay, we can have a little bit of a distributed load, and then how much the load we have. Say since we have eight, I would say total load W divided by eight to be in equilibrium. That's the one thing we can model that. See, we engineer, we need to be able to model the structures like this. Then we can solve. We can solve. It means that how much the moment distributions and then how much stress we have. Now is obviously the moment there will be a sort of a reaction force and moment, and then the moment we can solve that, but we can easily see that this is the where the moment maximum moment occurs. So moment wise, I think the will be like this. So very big moment here, right? And then decrease to the end. So no need to be a constant cross section because its moment is large. That's why we have a design like this, very the thicker here. You see that is a little bit thicker and getting smaller and smaller like this, right? So this is the that's why we need to learn the beam behavior. Beam, as I mentioned, being used for many structures. This is the one typical case. Then how this is the cross sections like this can be a circular. Let's say this is the circular. Of course, can be a rectangular, but rectangular is not easy to manufacture. The circular is easy. So you can see that this is a circular cross sections. But it is a really circular or with the same cross section, we may have a little bit of a elliptic like this. Why elliptic like this? Because this will be bending like that. So the up and down, we have a little longer elliptic type rather than transverse. So this is the effectively we take this structure can take over the moment, bending moment, right? So, and then again, the gradually decrease the cross section. Of course, we can make the just a straight, uniform, just the uniform cross sections. Uniform cross section, say big like this, then it's gonna be a waste of materials. We here we don't have a much, we don't need much cross section compared to here. So we always need to optimize these structures. So that's why gradually a decrease. Uh, to understand this one, we should be able to solve this beam problem and so on and so on. And by the way, this structure is made of the, not always, but better to be made of the carbon fiber composites. The Hang, E means electric, Hang means Hanghe in Chinese. Yihang's electric vertical takeoff and land eVTOL, such as the EV216S, are constructed primarily from carbon fiber composite materials, which is very light and very strong. Uh, the carbon fiber composites is the one which are used to make the say the bike, the uh, very high-end bike. This is all made of a carbon fiber reinforced composite rather than just the aluminum, rather than metal. So structure can be very light and very strong, and the maximize the performance. So solid mechanics, we also in our lab we are specialized of design of the carbon fiber composite 복합 재료. Uh, so the and this carbon fiber composites is the one we are using instead of a metal. Metal structure is a we don't longer no longer widely use, mainly for very special structures. So carbon fibers is very light, and the really future all kinds of structures will be made of the carbons, uh, fiber composites, and the oh, well, we Hanyang University HSCL Hanyang Structures and Composite Lab. Uh, we are that is our lab is a key research group focusing on carbon fiber composite. The lab led by Professor Song Ha and myself is globally recognized. Well, many good uh, words, but importantly, we integrate engineering and additive manufacturing, like the 3D printing of carbon fibers and fatigue and impact, specialized composite, aerospace and automotive, and industry university collaboration. Well, I didn't know they know this much, but uh, anyhow, we do a lots of research on the composites uh, and the hydrogen, tank and things. So the understanding beam, well, I didn't mean to come to here, but the understanding beam is important and also important to be able to design beam structures of any materials. Uh, and this eVTOL is the one of the typical structures. So anyhow, let's get back to, uh, oops. This is the my presentations about our lab. I don't know why this is open, but well, since it's open, I just like to mention that. Uh, oops. So this is our lab. We are making, this is a hydrogen society. You know the hydrogen, 수소, but we similar to a battery, we need hydrogens to power our structures, so which have to be made of the carbon fiber composites. This is the our lab. We make all the carbon fiber structures, and this is the a video. We can see that we make the structures and also all different types. Uh, Design and manufacturing and test is important, and this is the newly developed by the our lab. We do this is a carbon fiber tape. We use this laser automatic. This is a robot, and we layer the all the structure. Imagine that we have a beam. We make the beam. How can we make the beam using the carbon fiber? And we are using the all kinds of robot system. Uh, Robot to develop this robot. We simulate how the robot move, and this is the automatic tape. We have some head, and this is a tape supplying system, and we have a laser with the yellow line. That is the part we developed. It is one of the very well uh, developed product in the world. So anyhow, we are using these structures and to make the all types of carbon fiber structures. Well, I so anyhow, come back to here. We should be able to design that. I hope that you from this example, you get the idea why we are learning the beam theory. This is not a very typical application. This is just one of our applications, and then really widely used of this kind of beam theory. Well, we can go through the all the slide and the study about the all types of theory. Theory is important, but more importantly, how to make use it. We're gonna study more about the beam theory applications using the AI tools, which we'll cover today. Say, I just like to make the one comment, for example, uh, how to use a beam theory in the design of, say, eVTOL. Uh, well, I didn't mean to. This is just the one subject. Let's say this is myself even first time to give a prompt to the AI and see what it says. How to use a beam theory in the design of a eVTOL, right? Well, of course, there are many different types of eVTOL, and the keyword is eVTOL and beam theory. The beam, of course, they will this AI will look for the beam structures in the eVTOL. Uh, they even go to a very detailed subject. Um, this is called prompt. Prompt is the one you the communicate. So, well, it says great questions. Beam theory is the everywhere in eVTOL. Do you see, guys, this word? So below is a compact and practical guide you can drop into early sizing and trade study, rotor and prop blade, rotor and propeller blade, rotating beams with a flap wrap torsion coupling, centrifugal stiffening. Well, we can come back here, but the say landing gear, flame, and spar and boom. This is the one of the structure we are considering. Primary bending and torsion. This is a spar and boom. That structure is called boom. And some fuel cell or battery racks open the behavior like the beam. And so the what beam model to use? We have this is a torsion. Of course, they can subject to a torsion, not only the beam. And you see the EI. So we always need to start with identify the load and the idealize the geometry. That is called modeling procedures. And then get a EI as a function of X, and GJ is a torsion. I didn't mention the torsion, but the structures can twist like this, not only bending, but also it can twist. And see the strength of a stiffness, the bending stress over, this is a moment divided by I. This is how we calculate beam and torsion as well. the buckling stability, which we didn't cover yet. But once we have all the stresses, we should be able to design something. And 1 minute sizing. So sizing means the design. Once we know all the load and this, and we calculate the deflections, and EI should be something like this, and this, and sizing again is a design. Okay. And composite specific note. See this. AI already know most of structures are made of composites. So layup, you see the layup, we layer the fibers and things, and the joint, this and what to check before freezing design and so on. Anyhow, this is the real design steps, not just for simplification. This is exactly the step they take to design in the real world. And the So anyhow, this is the one application we can study. Uh, oops. Okay. So let's back to the main structure, main subject. Uh, so to combining all the equilibrium and bending moment, the curvature relations, so we get the force order differential equation. I like to simplify the procedures. The say moment plus V equal 0, and well, start with say V plus Q equals 0. Well, this is the equilibrium. This is a simply differential equation plus Q. This comes from the y-directional force equilibrium. You can say that derivative, a little bit of an increment is will be Q times dx. This is very obvious. Say Q times dx is what is that? Say we have a beam, we have a Q downward, then this Qx dx giving us the force over the dx, right? So this is the force downward, and then left-hand side we have a Vx, and the increment of Vx plus dx, dv. So what does it mean? This is the okay, sorry. This is the V upward, and the left-hand side V downward. So this one, this dV should be same as Qx dx, right? This is the same. This dV increment of vertical force should be the same as the Q dx. Very simple. And this is the one, right? You can have a dx and you can get this. Now, another equilibrium is that, what is that? Moment, z equals 0. So the moment on the left-hand side, you would have a like this, and also on the right-hand side, there will be some sort of increment, right? Now this guy will moment. So this increment will be dm will be same as this Vx times this guy, this V and this V makes it rotation, right? So the V times dx will be should be the same as the d moment. So moment increment should be the same as the V dx. So that's why we get this. Well, the it's not that difficult, but very important. These are two equilibrium, vertical equilibrium and moment equilibrium give us these two equation. And now another one, very important, moment equal EI curvature. What is a curvature? Well, EI V double prime. That's the what theory we learn, right? The curvature uh, is a simply a double prime. So combining all this, so this is the moment equal EI V. V is the deflection we like to solve, double prime. So we put this one to here, we put this one to here, and then you can see that this one derivative and put it here, another derivative. So to make the whole procedure short, we have 1, 2, 3, 4 equal Q. See, this is the one differential equation we can solve. So as long as you have a Q in terms of a function of X, and we giving the EI, and we get the V. This is exactly what we have here. EI V derivative equal Q. This is the one, which taken care of all the procedures. EI is a given, and QX is a given load. What we like to find out is a V. So how to solve it? We just consider this. And this one already have everything. Everything is already in there. So once we solve this one, we don't have to go every time equilibrium and this. Why? Because this equation already have all the different equilibrium equation inside, and already have all the curvature. I would say, this is the moment equal EI V double. We already have everything here. This is the one. So to make the whole procedures very, very simple, and one equation is like that. Okay, this is the really the strong message I like to emphasize, and the with the understanding whole picture in mind, but you solve this differential equation. That's it. The Okay. Uh, I know you a little bit bothered by the solving all differential equation, but you don't have to worry. We have a very nice tools, solver, differential equation, and AI and ChatGPT or any tools. Don't worry about that one. Uh, as long as you understand the whole procedure in mind, uh, there is a lot of tools. So all you need to do is just the understanding of a flow. What are the considered? What are the key steps? That makes you uh, the best designer of the structures, eVTOL and automotive, in airplane, everything. Okay. Actually, that's the one I like to emphasize in this chapter. This is actually the last chapter, last point. Now, to solve this one, I repeatedly emphasize to solve the equation, what do we need to have? We need to have a boundary conditions, right? To solve the differential equation, what do you need to do? I mean, mathematically, I'm sure that you learned this differential equation, how to solve that in 공업수학. The most important is the boundary condition, right? So differential, this fourth order, 1, 2, 3, 4, fourth order differential equation. How many boundary conditions do we need? 4. Always a 4. Then we have a 1, 2 here. We have a 1, 2, always a here 2, here 2. That's the concept you need to understand. Okay, I don't want to just study the mathematics and mechanics, but I like to emphasize we as a mechanical engineer, we need to contribute to a society. How can we do that? Well, with all understanding of a game theory and then able to design, we can make the eVTOL lighter and safe. And that's what we contribute to a society. And that makes you a strong engineer. And you can make the enjoying contributions, not just for the making money, but once you have all the, able to design and as an engineer, you will be needed. Everywhere will need you, and that's the way you can contribute to your knowledge and experience, and also your innovations. Okay, so the next one is the pretty much simple, and this is already we mentioned force and moment equilibrium. And this is the what we get, and this is the all the the calculation of internal force. The internal force is that every cross section we have a moment and v. That's the one you need to understand. That is called internal force. Don't consider what the hell is the internal force. It's not difficult subject. Say simply we have a beam, the bar, and subject to say we have a bar. It's very simple and very difficult. And then what do we have? We have a reaction force at the left from equilibrium, right? Once we have this, what do we have here? We have this is the F, you apply F, there will be a F here, and F here, and here you will have a F here. That is the internal force, nothing else. So everywhere you have a certain force. That's the kind of to register this force, each cross section will have to take over the load and then to support that load. With the understanding of this, and also with the understanding all kinds of the beam, exactly same concept. Here you would have a say sort of how much the shear force and how much the bending moment we have. That is the internal force. And this is the moment we already solved from EI, V double, the first order. And once we have a V here, and moment will be just EI double prime. See, once we solve the V, then we just double derivative again, we'll have a curvature and we'll have a moment at any cross section at the x, right? This is the procedure, so you need to understand. So this is the internal force. And once we have an internal force, then we have the stress like this. So this is the stress, maximum stress applied to a beam. And this is the one which can break the material. Why? Because we have a stress strain curve always like this, and this is the yield strength. So any material in any point, the stress reach this one, then material start to fail. Yield, plastic and structures no longer function as a structure. So all the stress have to be less than this. So we should design, considering sort of a safety factor this much. So the stress have to be less than here, or as the loading and unloading like this. So if we have the EV toll like this and vertical load and the maximum here, the stress will be always, the stress should be within these ranges. That's what we do. Well, design-wise, let's say the stress will be very small here, only this part. This is not good design. Why? Because we are wasting the material. And if we have a very thick, then stress will be very much small. And the stress will be only small portion of the material capability. Then it's a bad design. You as an engineer is not a good engineer. Okay. Point is that you everywhere you should this structure have to be maximized. But safety enough. So this much. Then we can minimize the material and then we can make the safer structure. That's the whole concept of the design. Don't waste your material. Okay, don't waste your material. Otherwise, this structure will be very heavy and the waste of materials and no longer competitive. To win in the market, how can you design structures? Lighter and small material, but very safe. Okay, that's the final goal. But as you can see, whole theory, I mean, the starting point is to understand beam theory. Okay, uh, that's what I like to emphasize, the internal forces, how to get the stresses, and we already covered this subject. Again, it's repeatedly the same point here. And so we have some simple case. Simply support it on the left and right. We will come to this one. Don't worry, we will cover that. But the important point is that always the boundary conditions and then differential equations. Then, as you can see, that how can we mathematically express the boundary condition? Well, since we are solving EIV 1, 2, 3, 4 equal QX, the clamped V is a deflection, so a deflection should be 0, and the slope is clamped. Clamped means that it doesn't deflect like this angle. right? No angle, no rotation is allowed. So V prime, what is a V prime? This is a slope and it should be zero. So clamped, we always say deflection and deflection is slope is zero, and also is also clamped. So on the L at the L is a deflection zero and the slope is zero. And if this is the simple support like this, then what is that? The deflection should be zero, and also another boundary condition is the moment equals zero because it's allowed to rotate. So moment equals zero, okay? Moment equals zero, but what does it mean? Moment equal EI V double prime. So moment equals zero means that V double prime equals zero. Very simple. So once we have this problem, then you have a mathematical solving tools you can go, or you can just by hand integrate step by step. You can get the all the integration constant. This constant will be obtained using these four boundary conditions. I don't want to be going through these all the procedures. Now you have a very wonderful tools like the ChatGPT or Excel or any differential solver. Okay, so the one thing I like to emphasize here is that the as you can see, boundary condition. Okay, so to solve this one, EI V1, 2, 3, 4 equal QX. V is of course represent deflection. And what is a V prime? V prime is the angle of rotation. The V is given, and the slope. Okay, slope is like this. So this one is the V prime that represent the rotation. So V prime is the angle of rotations. What is a double prime? Well, we know that, okay, this is the one, and moment equal V double prime. So double prime is that represent the curvature, is a moment. And now what is a triple prime, three times prime? That is the shear force. See, the point is that we are trying to solve the force of the differential equation. We need a conditions at deflections, okay, deflections, and the zero prime, first prime, double prime, and third prime, and then we have say 1, 2, 3, 4 equal QX. So what is a triple prime mathematically? Well, in equilibrium condition, we already know that the moment derivative, we already have this one, right? So once we have this moment, we'll put it here. The V will be triple times because this is the second derivative. We have one more derivative giving us the shear force. So shear force will be given like this, V triple times derivative. So the reason we are paying attention to this one is that since the carbonication is given like this, so we need to specify the boundary condition in terms of either V, 1 prime, twice, and 3 times. So this is just a mathematical representation, but mechanically we need to understand this one. So now to do so, we need to understand the boundary condition. Simply support like this. While V is unknown, we don't know. We don't know the V. Shear force, we don't know. But what we know is that V deflection equals 0. Then moment is also 0. So we know the moment equals 0 and deflection is 0. Moment 0 means that double prime is 0. So this is a two boundary condition at the simple support. Clamped, what do we know? We don't know the V, we don't know the moment. Means that the reaction force, we don't know. But we know that geometrically, the slope will be 0 and deflection will be 0. This is a two boundary condition. And sliding, well, this is a not a common boundary condition, but let's say we have a sliding, freely sliding. But as you can see, the slope is this one. Slope would be 0. So shear force is 0, and then moment we don't know. But moment is we don't know. As you can see that the slope, it does not change. So prime equals 0, and the shear force is 0. So 1, 2, 3 equals 0. So as you can see that simple support, this is the one, this, and clamped this, and sliding this. And actually one is missing is the free boundary condition. Free means that just a free, nothing there. So we know the V equals 0 and moment equals 0. V0 means that what? 1, 2, 3 equals 0, and moment equals 0. What does it mean? Double prime is 0. So any boundary condition, mechanically or mechanics-wise, we can get the two boundary condition at each end. That's what we like to say. So this is a summary. Clamped, deflection 0, and slope is 0. Simple support, deflection 0, and the double prime is 0 because the moment is 0. Free boundary condition, moment and the shear force is 0. So double prime 0, and then triple is 0. Okay. And and additionally, we can have a sort of applied concentrated force. Let's say we apply instead of a free, we can apply certain, the shear force and bending moment. Then we can simply say, V equal P0. This is a real known value. So since we know that V is that, what is that? EI V 1, 2, 3. So this is a shear force. So shear force is a vertical load. This is a given. So we do know the triple prime. And moment is specified. Well, we already know moment equal EI double prime. So we know this one. Pretty much straightforward mathematically. So engineering-wise, we understand mechanics and then relate to a mathematical relation. We should be able to represent our mechanics in terms of some mathematical representations. Okay, this is a very important slide for you guys need to understand. Okay, so calculation of beam deflections. So when you predict some deflection, I just want to say this is a rotation, right? Rotation, beam will not deflect like this. Always the vertical like this, or always. Okay, so it should be like this, and then like this. This is the one we should be able to predict. Very important. Why is it important? Because we are dealing with the differential equations, and we should be able to to imagine, visualize a V, which will help us and understand all the stresses and so on. So I don't want to go through. I don't need to go through all the the integration and integration coefficient, and another integration will give us C1 V C2, and another integration we have another C3. Another integration. You know how to integrate them. And left hand side always starting this equation, right? And then one, two, the integration, how many? One, two, three, four. These four integration constant will be obtained from these four boundary condition. One, two, three, four. That's mathematically very much straightforward and simple procedures. Okay? Well, uh, I know it's a little bit new to you, so uh, it can be a little bit difficult to follow, but don't worry. It takes time, but you need to repeatedly drive and then solve and then think, you know. Uh, so everything is just mathematical. Well, there is some singularity function to define. Uh, let's have a 10 minutes break. Okay, this is a 2:15. Let's come back on 2:25. Okay. Oh, very sorry for the urgent meeting calls. Okay. Well, mm, okay. This is the share the okay, recording. Okay. Now, one thing we still need to cover in using this fourth order differential equation is that how to represent the load in terms of a distributed load Q. Okay, this is the differential equation, right? Uh, and one thing again is now we got all the boundary condition and no problems. And the one thing we need to learn more is the this distributed load within this range. Now the Q is again the distributed load, load per length. If this is a uniform, it's very simple, and we can say Qx is the Q0. And if this is a linearly varying like this, we can express this one in terms of x, like a linear. And if it's again linear but with a non-zero the value, we can do this. Now, if the load is the not uniform but can be applied like this with a the non-continuous function like this, so then Qx can have a specified at different regions, 0 and Q0, something like that. Okay, this is the one. And also a concentrate load, this is one important point. Concentrate load is not the same order as a different distributed load. So to mathematically, we can use the delta function. Well, delta function, I know it is not the conventional mathematical equations, but here is the just the simplicity, expression simplicity. That's it. And also this one and this. As you can see, 0 and -1 and -2. Well, you can say many order. Again, don't bother with with this function too much. This is just the simple mathematical equation to represent this kind of a non-continuous one and this concentrate. So this one you can see if we change this concentrate load like the distributed load, we can express like that, right? And 0 and some value and 0 like this. And moment is the same thing, sort of this and like this and 0. So mathematically, this is the way we can represent. Okay, 0 means that anything, say this is a negative, say x less than a, this will be a 0. Anything's less than 0, which means that if x equal less than a, this will be 0. Same for the 1 and same for the -1 and -2. Then if x is greater than a, this will be simply regular parenthesis. It's simple like that. And this one, same thing, x minus a 1 equals 0 for x less than a. But the x minus x, if x is greater than a, then this will be just the x minus a square if x is greater than a. I'm sorry, this is 1. Okay, same like that. Well, we call them a singularity function. The reason we are using the singularity function to be a consistent, we can use this for further differential equations. Okay, this is the more in detail. This x minus a n power over n. Again, if x is less than a, then this is a 0. And if x is greater than a, this is just become the regular n. When n is a positive or 0. If n is the minus, less than 0, like the x minus a minus x minus a minus 2. And this will be simply like that. And this is when we integrate, we just follow this one. But remember that we can follow region by region. That's still okay. But just a simplicity, we follow this one. And it is greater than 0, then we integrate like this, and less than 0, just the n plus 1. If you again you just understand once, and then when you use that, you don't need to fully memorize them. You can just open the book, and then you can use this formula in solving any problems. But the understanding is more important. Okay. The way of calculating shear force and bending moment is that once we have the solve EI and QX and solve of V, then the equilibrium equations, differential equations, we can get all the procedures. This is really mathematical expressions, and there could be some special beam problem. This can be applications of what we are learning. Say this is the two beam, very interesting subject. Pay attention, please. Let's say we have a two beam, and then on the here we have a sort of a contact point, just a simple contact point, and then we apply the load P here. Then we like to solve. Solve means that we get the deflections over here, and also deflections over here as well, together. And how to do that? Engineering-wise, this can be very important. And the point is that we like to solve this beam and that beam separately. Let's say we like to solve this one. We have this, and we have a boundary condition. But the point is that we don't know how much force is applied at the end here. And this force will be exactly same as that one. This is the action reaction. And again, this F we don't know, but we do know this F, P. How to solve that? Well, the point is that even though we don't know this F, but what we know is that deflection, this much deflection and that much deflection will be the same. So let's say this is the V1 and V2, and V2L, okay, this deflection will be the same as a V1 at 0. This is the one condition we have to know. We have to use solving this one. And this is the way we can get the F unknown. So point is that this we just solve this equation with with this F. We don't know, but we just use that as a given value, and same for here. And so we get this equation and that equation in terms of F. Now, at the final, we use this one, we can get the F. Okay? So that is the point. And this is we can say a constraint. Okay? So another beam problem is that this is very typical. We have a simple support and clamped, and we have a P here, and carbon equation, and this load and Q in terms of a P using the -1. This is a concentrated load, and the two boundary condition and here and two boundary condition here we can solve. Just the starting here and then following these definitions of a singularity function with this is the final. And this C1, 2, 3, 4 can be solved from these two boundary, four boundary conditions. Okay. Well, we can solve differently, but well, this is another problem. We have one boundary and another boundary. We cannot say boundary, but there is another support in the middle of a beam. This is a little different from what we learned, but it's not a big problem. We can do, say, we separate them into the two beams like that, and then here and that, and we have a certain condition here, and then we can get the sort of unknown equation. Another easy way will be, say here, the point is that we don't know how much the reaction force, right? So we have a P and we have a F. If we know the F, we can solve this equation, I mean deflection curve. So we just solve them with the P and F, and then once we have all the equation, and one constraint at here is that V at C is what? Deflection at C is 0. Okay, so this is the way we can get the F. This can be a very important trick. And and another one is that this is all different types of applications. I mean, using the beam theory, how to solve it in general, and so on and so on. And then there can be some problem. Another case is that we have two beams with a different say EI, how to solve it when we have a P here. So we can separate them. We can separate this one and that. And here, sort of a unknown, then we can solve continuity. Here, always, if the beam is attached, okay, beam is attached, deflection will be the same, and the slope will be the same. That is the key point. Well, this is the another the application problems like this. If we have two beams and we apply the P load here, then how much the stresses and deflection? Well, the very similar to a previous problem. We have a AB beam here. We have a clamped, and we have a load. But the point is that this contact point, we don't know. Say, let's call the R. And then we solve this problem. Now the another one, this is the transverse like this. And then this one, we have a R here. This R is the same, but we don't know how much the this R is. So we can solve this problem, right? We can solve this one, we can solve this one once we know the R. So we do that. And then once we get all the deflection of V1 and V2, now here, the deflection of that point, deflection at that point will be the same. That's the one we can solve. So deflection 1 and deflection 2 will be the same. We can get the R. Okay, I just like to give a direction how to solve this kind of problem. So as you can see that all the beam application problem is that we sort of use some geometric constraint, uh, engineering sense. And this is also important applications. Say here, the K, we have a spring attached. How to solve that? Well, the V, we don't know the V, like the P here. And the V is the one, the force exerted by this spring. And this V is the also K, this is spring constant, and the delta. This is a spring constant. So V is the what? EI triple prime, and K. What is a V? Is the V. Delta is the V deflections. And the we need to pay attention to the sign. The V should be here. So here at this point, we do have a, say this is a R over 2, R over T. This is just one boundary, the condition at the middle. And from here, we can have we can solve this one. So this is all mathematics. And then I don't want to teach you how to solve the differential equation. But engineering wise, you need to know how to impose this boundary condition and the deflection condition and so on. And same for here. Okay, you need to get yourself familiar with these types of problem. I mean, the combination of a geometric constraint and the regular beam theory and so on. Okay. One very interesting problem can be, well, similar to the one homework. Let's try to solve this one. Say we have a beam, okay? We have a beam and subject to the distributed load. Let's try to solve this one using the ChatGPT, okay? Using your own ChatGPT and my ChatGPT. So the point is that I like to emphasize how you can use the AI. You know, AI is the unavoidable approach. You need to learn how to use that. It's not just the say you know the trick. It is you must know how to use that in many applications, of course, including our beam theory and the mechanics and the our course. So this is a Q, a kind of a distributed load. And now the point is that let's say we have a two simple support. This is some simple support. Let's say this is L and this is A. Of course, the A should will be less than A. And imagine that A is a little small. Okay. See the design A, very simple like this. What does it mean, design A? If A is too small, for example, you can imagine that A is very small here, like this, then this load will deflect like this, and you have a lot of a moment here, and then a stress will increase. If A is very small, and if A is very large, like this, then the moment deflect like this, and then a moment will be a maximum here. So this moment will be large, and this moment will be also large. So we as engineer, we can expect that the moment maximum with respect to A. Okay, this is the key point. If A is too small, like this, the maximum will be a large. If A is a large, then the also large. So we can estimate like this. If A equals 0, the moment will be very large, big, and L, if this one is big as well. Then we engineer like to find what is the A? I would say optimal distance, which would minimize the stress in a beam. Okay, give you 1 minute to think this problem. Just to fully understand this problem, you don't need to solve, but to understand the case of these beam problems, uh, and then, oh, this one makes sense because the sort of optimal A, then this one will be like this, and then a bending moment can say A optimal, giving us the minimum maximum. Sorry, the A. Sorry. The moment maximum can be minimized. Maximum moment can be minimized at A optimal. This is the point. This maximum can be minimized. This can be very practical, the case when you design this. You have a distributed load. You have a two support. Where you gonna put these two block? Okay. So this is the kind of a case. Well, I didn't try the solve this one using the ChatGPT, but let's see. Let's try to solve it together. And then the point is that we like to get used to the AI, how to solve the engineering problems. this is the real case. Say find the A again to minimize the bending stress. Okay, well, same as the minimize moment X. Okay, we have a ChatGPT. I know you guys know how to run the ChatGPT, but there are a lot of different feature of the ChatGPT. Say you can have programming and the all different types of features. But I don't want to go through in detail, but I just like you uh, give you a chance to get used to ChatGPT solving these types of mechanics problem. So say you are learning the fluid mechanics, dynamics, try to communicate with the ChatGPT. This guy can be even much, much better than, of course, I am, what I do, because this will combine all the intelligence, artificial intelligence, giving us the all the guide. So the again, these solid mechanics, as I described, you can share with me. You should have a project. You should know how to create a project. You just name, and then that's the what I get here. And then you can have a share with me. You can have a address like my address like this, and the I will get shared. I will get shared means that I can work together with. I can go through what you do in the same uh, so that is the one. And by the way, this can be one of your final term project. So try to learn very well. It's very important. Not only understanding all the uh, the solid mechanics and beam theory and all other application like the stress transformation and everything. You can have your own ChatGPT solver. Imagine that you have one project, okay? Have all different subject and tools. So you don't need any other tools. You just open it and then you give a direction and you can get the answer. But to do so, you need to understand beam theory and solid mechanics. What is important? So the I would like to say in now we are in the solid mechanics and the solve a beam with a uni okay, find the I will say A for a uniform loaded beam. Well, of course, the this guy would not understand what it means. This is called a plant. Uh, well, I didn't try, but let's try. Uh, say just copy rather than the describing. You can describe, okay, you can describe, but uh, say just copy. I hope the ChatGPT understand my handwritings. I just mentioned find the A for a uniform loaded beam, and then it gives the, something like that. Do you mean the distance to the inflection position in a fixed beam, and then so and so on? They just formulate. They try to understand by the prompt I gave them, but this is not quite right. But the reason I just mentioned is that give him a chance to get ready. This is the definitions of the problem. Let's see what it says. This can be a very typical procedures, right? Excellent. Does this sketch describe a beam with a uniform distributed load W? Well, they say W. Supported two symmetrical. Symmetrical is important. I didn't mention that, but they just noticed that is left and right is the symmetric on this part, this part. This makes this is exactly what I want, but this guy noticed that. The this will load W supported at two symmetrical points at each at a distance A from the beam end. So total span L overhangs on both sides. Overhang, okay? This is just a hanging. And you want to find the A that minimize the maximum bending stress. Okay, very good. This guy, ChatGPT, understand exactly what we like to solve. Am I right? So I know you guys can just sketch like this. Well, my handwriting is not so good, but very fortunately, this guy would immediately understand that. And then step one, okay, this is the one we like to learn from ChatGPT. Step one, beam length L, uniform load W. We usually call Q, but they said W per unit length. Per unit length is important because it's a distributed load. And support located symmetrically at a distance A from each end and overhangs on both ends each length A. The central span between the support L minus 2A. Well, say explain Korean. Oops, Mrs. Pell. Well, he just they understand even with the Mrs. Pell. 어, 양쪽 끝이 오버행된 균등 하중 W를 받는 보의 문제. 전체 길이가 L, 양쪽 지점 끝에서 각각 A만큼 떨어져 있을 때 N-의 최대 힘 응력 또는 최대 모멘트. This is a really important point. 응력 maximum stress is the maximum moment. 최소가 되도록 A를 구하는 문제. And this. See, we can certainly go through, but the more important point is that we fully understand how ChatGPT understand our problem. Otherwise, the derivation and this is no meaning. So this is a problem statement, beam length, and the equal 단위 하중 W, and so on. And this is our objective. Since this is a symmetric, something like that. Okay, right? So I just copy this one to you guys. You can easily see in your own ChatGPT. So anyhow, uh, and this is the reaction force is important. Reaction is that at the here and there. Since we know the total force, the each reaction force will be the half of the total force, right? Half of the total force. And the mid span between the support, between the support, middle span means here we have a moment here, and the find the A that minimize the moment maximum here. Okay, mid span at support, a negative moment, and then solve. This is just a mathematical, and uh, A will be this gives a minimum. Wait a minute. This solution doesn't look like a right. A A is too small. The support are near the ends. Large mid-span moment, and A is too large. The span between the support is short, but the overhang create a large negative moment at the support. See the support at the near end. Okay, this guy misunderstand. 이 양쪽 지점의 이 끝에서 각각 A라고 했는데 우리는 양쪽 끝이 아니라 이게 중간 A죠. 양쪽 끝이 아니라 중간 A. 그래서 이게 우리가 말로 잘 표현해야 되는데 그림이 얘가 약간 오해를 했어요. 자, 이게 베로 티피컬한 현상입니다. 그래서 얘가 잘 이해를 했는지를 봐야 되는데 그래서 too small이면은 이게 중간으로 오는 거고, 또 support near the end, 이거 지금 틀린 말이잖아. small 하면은 support가 어떻게 돼요? 가운데로 오는 거죠. 어, 그럼 어떻게 해야 돼? Well, pay, say, careful attention to the definition of A. A is the distance uh, between the uh, central parts. So I'm very glad the ChatGPT give us the wrong information. Okay, I'm glad that I didn't mean that, but I'm glad we have this chance. 아, 정의가 바뀌었군요. See, ChatGPT misunderstand this A. They misunderstand that A is outside, but our A is the middle side, right? So A는 중앙부 두 지점 사이의 길이 전체 길이에서 이렇게 된다. 이렇게 돼서 A가 0.578 정도의 길이다. 57%. 자, 그러면 이게 어떤 의미가 되겠습니까? 어, 어바 비슷하게 맞지 않겠어요? 이만큼인데 57%면 중간쯤에 왔을 때, 밴딩 모멘트 스트레스가 미니마이즈 되는 거예요. 자, 계속 질문해도 됐습니다. 좋습니다. 어, we like to better understand the effect of A on the maximum moment. 뭐냐? We like to better understand the effect of A on the maximum moment. Okay, so plot the say uh, okay, the maximum moment versus A. 우리가 아까 그림으로 대충 스케치한 거 있죠? 대충 스케치한 거 이거. 이게 모멘트가 A가 0이면 커지고 L일 때 커지는데 중간쯤에 이거를 대충 이렇게 이해했는데 얘가 좀 얘네들 보고 챗 GPT 보고 정확하게 We like to better understand the effect of A on the maximum moment. So plot the okay. 그래서 you can use any well just say this much and then see what it says. See our intelligence, our understanding, and with the AI intelligence, we combine them, we get the better equation and better result. See, I'm sure it takes a little more time because the we like to understand the effect of A means that we like to okay. So effect of a central A on the maximum moment. This is the moment. 이 그래프는 중앙부 A 오버 L, 그러니까 0부터 1이 되겠죠. 다른 최대 힘 모멘트가 변화를 보여준다. 왼쪽 AL이 작을 때 지점이 중앙으로 올리며 어쩌고저쩌고 0.57 부분, 0.57이 여기에요. 이게 매우 인트레스팅하게 리얼치 줬는데 총 길이가 0. 그러니까 얘가 지금 여기라고 하는데 아니 여기가 있는데 왜 여기를 미싱했을까? In graph, uh, there is another point which would uh, mini minimize further. 그래프에 분명 요점이 더 있는데 왜 여기 0.57, 577에 지금 이게 여기를 끄집어 놨느냐라고 지금 질문을 하는 겁니다. 아, 내 생각에 얘가 아마 중앙에만 구한 것 같아. 어? 이게 바깥쪽으로 갔을 때 바깥쪽을 안 풀고, 그러니까 지금 정답이 한 7쯤, 미 그래프로 나와야 되는데, 좀 오래 걸리네, 얘가. 음, great catch. My earlier misspan formula was off, which is why the first plant hinted on a deeper minimum. Elsewhere, I have corrected it and then re-plotted. Support negative moment magnitude like this. The 어, 오케이. 이 결과를 보면은 지금 대시드가 지금 그 대시드가 뭐냐면요. 요거를 좀 크게 봅시다. 이게 지금 그래프가 지금 이 도트 라인이 있고요. 도트 라인이 미드 스팬 안쪽에 this minimum occurs at 미드 스팬이고 좀 이렇게 long dotted line 요 라인입니다. 요 라인이 서포트에서 일어난 거고요. 그 다음에 maximum of the support and mid span will be 야, 얘 자꾸 이 미스테이크 하는데 지금 이 그래프에서는 분명히 요 포인트가 헬프 여기가 지금 그 어, 정답이어야 되는데 그렇죠. 여기가 근데 지금 요 중점에 여기를 잡고 있는 이유가 그러니까 모멘트가 네가티브가 될 수도 있고 파지티브가 될 수가 있는데 그거를 얘가 생각을 못하고 자꾸 파지티브만 생각을 한 것 같아요. What I meant by the maximum I would say should be from the absolute value. 그러니까 절대치. 그러니까 최소가 됐든 그러니까 마이너스가 됐든 플러스가 됐든 그래야 된다는 거가 한 가지 그 미싱 된 것 같아요. 어, 봅시다. 그러니까 지금 아주 그 중요한 나는 결과라고 보는데 챗GPT를 해서 우리가 정확하게 스페시파이 할 때 이게 우리들이 갖춰야 될 아주 중요한 스킬입니다. 어, 지금 모든 거를 다 100% 얘한테 스페시파이 하기가 처음에는 힘들어요. 뭐 간단히 스케치를 했습니다. 반드시 you check it out and you confirm and see whether you understand well or not. That's a very important step. 그래서 지금 일단 결과를 보고도 얘기하는데 maximum should mean that maximum of the absolute bending for a uniformly bending. 자, 얘가 조금 뭐 가리했는데 어, 오케이. 내가 좀 내가 잘못한 것 같으네. 이 도트가 미드 스팬에서 일어나는 맥시멈이고, 그 다음에 바깥에 이 큰 도트, 이거는, 서포트에 있어라는 모멘트이기 때문에 전체 맥시멈은 이게 아니라 이거네요. 이거에서 다시 이쪽으로 가니까 요게 0.586이 지금 맞습니다. 오케이. 제가 그림으로 다시 이제, 이해를 좀 그려볼게요. 자, 어쨌든, 지금, 이게 100% 우리가 이해를, 하는 게 지금 중요한데, 여기다가 복사를 해서 봅시다. 저 뭐 수식도 있지만은 그래프로, 쉽게 이해를 하면은, 옵스, 스마일 펜인데. 아, 자, 여기서 우리가, 이렇게 돼 있고요. 이렇게 지금 돼 있습니다. 지금 분포화 중이. 자, 이거 하나를 이해하면 우리가 앞으로 이 챗GPT를 써서 많은 그 미케닉스 문제를 풀 때 매우 도움이 됩니다. 자, 여기서 이게 지금 A입니다. 이건 아까 커렉션 시켰어요. 자, 여기 보면은 모멘트의 노멀라이즈드 모멘트라는 게 이게 절대치를 얘가 이제 뜻합니다. 맥시멈 이걸로 노멀라이즈 시켰다, 그 중요하지 않고. 그래서 맥시멈입니다. 맥시멈, 뭐, 절대치를 취했어요. 이것이, 이두 가지를 봅시다. 요걸 먼저 봅시다. M 미드 스팬. 그러니까 안쪽으로 돌았을 때 모멘트가 지금 이게 여기서, 자, 하나 더, 얘한테 좀 요청을 해야 되겠다. 뭐냐 하면은, 이렇게, 왜 안 들어갈까? 왜 안 들어갈까? Okay. Say, please plot the uh, moment distribution uh, over the length for the optimal A. 지금 뭘 하려고 하냐? 좋아. 이게 지금 찾았는데, 이 A일 때, 모멘트 디스트리뷰션. 그러니까, 모멘트가 길이의 변화에서, 길이에 따라서 어떻게 변화하는지를 한번, 플러스 한번 해보라고 하겠습니다. 그걸 놓고 이해를 하면은 우리가 좀 더, 해서 설명도 쉽고 이해가 지금 더 좋을 것 같아요. 자, 다시 이제 문제를 우리가 정확하게 표현을 하고, 아니, 그러니까 이해를 하는 게 중요한데, 너무 가까이 오면은 어떻게 돼요? 밴딩 모멘트가 그 지지점에서 일어나고, 이게 벌어지면은 밴딩 모멘트 맥시멈이 어디서 부러질 것 같아요? 중간이죠? 그게 지금 포인트입니다. 이게 벌어지면은 중간에서 맥시멈이 나오고, 이게 너무 이게 좁아지면은 바로 그 지지점에서 나온다는 거예요. 그게 지금 핵심입니다. 그래서 요게 A가 어느 정도에 있어야 되는지를 우리가 풀어내는 건데, 어, 지금 이거를 몇 번의 대화를 하는 이유는 이게 정확하게 우리가 프롬프팅, 그러니까 글로 쓰고 표현하고 뭐 하는 것들이, 얘가 정확하게 이해하게 던지는 게 매우 중요한 기술인데, 그거를 좀 기술이 좀, 필요할 때, 혹은 모자랄 때 이렇게 간단하게 던지고 체킹하고 던지고 체킹하는 게, 있을 수가 있습니다. 오케이. 요 그래프가 매우 이해하기가 쉽습니다. 자, 아까 다시 문제로 돌아가서, 이게 뭐 맥시멈 미니멈을 떠나서 아까 A가 이렇게 찾아졌죠. 어, A가 이렇게 뭐 심볼릭하게 딱 나왔네요. 이게 A입니다. A가 이 L에 대해서 E 마이너스 그러니까 En 마이너스 루트 이니까 이게 뭐 1.4 하면은 해서 이렇게 지금 딱 나온 겁니다. 그러니까 0.5 어쩌고저쩌고 나왔죠. 자, 여기에 이제 분포화 중 모멘트가 이렇게 가니까, 예? 이렇게 지금 모멘트가 가해졌을 때, 오케이. 쏘리. 내가 여기다가 밑에랑 맞춰서 그림을 그릴게요. 이렇게, 여기다가 이렇게 해서, 모멘트, 이게 이렇게 되고, 여기에, 어, 어, 오케이. 서포트가 여기에 딱 있을 때입니다. 그렇죠? 그 다음에 분포화 중이 이렇게 지금 돼 있는 경우에요. 그랬을 때 모멘트가 어떻게 되냐? 모멘트가 여기에서 빵이에요. 이게 모멘트가 아무것도 없으니까. 그다음에 네거티브로 쭉 가고 여기서 지금 이렇게 돼요. 그러니까 지금 모멘트가 이렇게 된다는 얘기입니다. 모멘트가. 그럼 이 값이 있을 거 아니에요. 여기 지금 상상을 해보십시오. 이렇게 딱 하면은 여기에 최대 모멘트가 걸리겠죠. 이게 부러질 것 같죠. 예. 이렇게 되고 그 다음에 또 중간에 또 어떻게 되냐면 이 하중이 있으니까 이게 또 이렇게 쭉 올라가. 이렇게. 그 다음에 다시 이제 시메트릭하게 되는 거예요. 그러니까 맥시멈은 뭐냐? 여기 아니면은, 여기 아니면은 여기다라는 얘기예요. 그러니까 이게 좀 더 벌어지면은, 이게 약간 더 벌어지면은 어디로 가겠어요? 맥시멈이 이렇게 돼서 이렇게 나오고, 어? 맥시멈이 이렇게 돼서 이렇게 커지겠죠. 이렇게. 그러니까 이게 아주 커지죠. 그리고 좀 더 안쪽으로 들어오면은, 이게 안쪽으로 들어오면 어떻게 되겠어요? 이게 이렇게 커지겠죠, 안에가. 그 다음에 위에는 또 살짝 이렇게 되겠죠. 그러니까 이게 너무 커진다, 이거. 그러니까 A가 이쪽 너무 벌어져도 안 되고, 너무 절어져도 안 되고, 여기 딱이면은 이제 이렇게 돼서 요 놈과 요 놈이 딱 같은 거예요. 지금 이렇게 보면은. 딱 같고, 여기도 딱 같고 해서, 그 값이 이렇게 딱 수치적으로도 나온 겁니다. 그랬을 때 여 값이 그러니까 우리가 구하고자 하는 여 값이 a가 2 마이너스 루트 2. 나 이런 수식도 처음 봤는데 어 이게 그러니까 아까 얘기하는 0.1 14니까 0.뭐 한 5 아까 얼마였어요? 7 뭐 이렇게 된다는 얘기예요. 아주 좋아요. 이렇게 해서 우리가 이 솔브 문제를 풀었습니다. 자, 우리가 AI를 가지고 이게 뭐, 치팅하는 것도 아니고 카핑하는 것도 아니에요. 우리는 이제 AI랑 같이 살아야 됩니다. 그러기 위해서 우리는 이제 일단은 어떤 서브젝트든 간에 그 서브젝트를 이해를 해야 돼요. 그 다음에 가장 most intelligent한, AI와 같이 대화를 통해서 문제를 풀어나간다는 이 컨셉이 이제 엔지니어로서 우리가 이제 익숙해져야 된다는 얘기예요. 중요한 메시지라고 봅니다. 뭐, 구태의연하게 혼자 풀어라, 왜 복사했냐, 왜 카페냐, 이런 거는, 아주 옛날 얘기고, 이제는. 앞으로는 이제 이러한 이게 툴이에요, 이제. 여러분들이 항상 손에 있는 툴입니다. 그러나 중요한 거는 그냥 얘한테 던지고 그냥 받아내면 아까, 교수님이랑도 똑같이 했지만 계속 실수가 나와요. 실수가 나올 수 있습니다. 이거는 바람직하지 않아요. 그러기 위해서 여러분들이 첫 번째 먼저 이해를 해야 되겠다. 그 다음에 문제를 잘 얘한테 던져줘야 된다. 그게 메시지입니다. 그래서 우리가 저도 지금 챗GPT랑 처음 해서 내가 처음 하는 이유는 챗GPT가 나오는 이런 리스폰스 이런 것들이 여러분들한테 직접적으로 경험을 보여주기 위해서 내가 미리 한번 안 해봤는데 이러한 과정을 통해서 우리가 아마 문제를 풀면은 내가 혼자 풀어도 한 네다섯 시간은 걸릴 거예요. 그런데, 가이드를 받으면서 한 10분 내로 풀 수 있다는 거. 앞으로 여러분들 이제 똑같은 메시지입니다. 그러기 위해서 여러분들이 빔 티어리를 잘 이해를 해야 되겠다라는 게, 포인트입니다. 오케이? 그래서 지금 내가 한 거를 그대로 지금 링크를 줬으니까 한번 스스로 여러분들이 이제 여러분들 챗GPT 한 거 있죠? 요 프로젝트 여러분 만들어 놓은 거 있죠? 여러분들 거 지금 나랑 공유를 좀 하세요. 여기 공유하기 여기서 누르면은 이제 나한테 이메일 주소 하면 내가 여러분들 과정을 관찰할 수가 있습니다. 그래서 이 과정을 잘 하세요. 지금 이게 텀 프로젝트가 될 겁니다. 여러분들 시험의 과정으로 이렇게 진행을 할 겁니다. 그 시험해서 뭐 여러분들한테 스트레스 주고 이렇게 하는 게 아니라 얼마나 중요하다라는 메시지를 여러분과 같이 시어를 하고 싶습니다. 아셨죠? 이제 패러다임이 바뀌어야 돼요. 우리가 엔지니어링 문제를 푸는 데 있어서. 자, 오케이. 여러분들 만든 이 챗GPT를 가지고, 좀 연습을 많이 하고, 호목도 그렇게 내겠습니다. 어, 그, 오케이. 지금 4시입니다. 아까 내가 조금 쉬는 시간에, 시간이 허비됐는데, 지금 딱 4시입니다. 수업은 여기까지 하고요. I hope that, get used, get a chance to a new way of solving engineering problems. ChatGPT's unavoidable approach. Uh, uh, so that we can get a better result and with a faster, with a less time. 오케이, 수고 많이 했고요. 자, 아마 다음 주에 내가, 녹화된 거나 좀, 수업을 다시 어나운스를 할 수 있을 것 같아요. 그럴 경우 내 메시지를 넣겠습니다. 오케이, 수고했습니다. See you next time. Bye.